Would be arrested. Okay, so let's get started. Um, so last lecture we um, moved on from talking about prepositions to predicates, right? So to remind you, predicates, uh, while prepositions are simple and you can just think of them as true or false. Prepositions, predicates have additional parameters, and you have to specify the value of these parameters. And at that point, you will know whether uh, the statement is true or false. Okay. So the difference between prepositions and predicates is that you have to first specify the value of these parameters before you can say something is true or false. Okay. And once you have these parameters, then we talked about quantification of these parameters, where you can say something is true for all values of the parameter, or something is true for a particular value of a parameter, right? So where we say there exists a value for which this statement is true. Okay, so we come back to this. Let's pick up uh, where we left off. So we wanted to take a statement which is what we call as gold box conjecture, which basically says that every even integer greater than 2 uh, can be expressed as a sum of 2 primes. Okay, so then we said that for all n, right? So we said that for all n, right? The requirement is there only for n greater than 2 and n being even. So we state that condition. So we say that if n greater than 2 and n is even, then we say that there exist 2 prime numbers, okay, or rather 2 natural numbers p and q, such that both of them are prime and n equals p plus q. And after giving this example, we started talking about the order of quantifiers, right? And we said, okay, if here the for all occurs outside and there exists occurs inside, which means that after making a particular choice of this n, so we said that after making a choice of this n, then you can decide, what is the value of these p and q, right? So that's why the fact that the, these there exists operator is inside means that it can make the choice of the values for p and q after n has been picked. So you can think of the quantifiers deciding the values of parameters going left to right, right? So the leftmost parameter is the one that you decide that you pick first, and then you go inside gradually. So if you change the order, then it doesn't make a lot of sense, because what it says is that you first pick p and q, right, such that this p and q will work for all n, right? In particular, for any n, that n can be expressed as a sum of this p and q, right? So that obviously does not make sense at all, because once you pick p and q, that uniquely determines what is p plus q. And so that's so therefore you cannot have the there exists appearing before. So not that I think more of you can turn on your cameras maybe, so I can get a little bit more of a feedback. Thank you. So let's explore this order of quantifiers a little bit more carefully. So the point we made last time is that if you have two quantifiers that are of the same kind, then you can interchange their order. But if you have two quantifiers that are different, as in this example where you have a for all and then a there exists, these are two different types of quantifiers, then one order may make sense, or in the sense that one order may yield a formula that's always true, another order may yield a formula that's false or only sometimes true, right? So that's the example we saw. So so we have to be careful about the order of quantifiers. A related point is about what happens when you negate quantifiers. Okay, so let's try to take statements like this and turn them into quantified formulas. Okay, let's take this example. Not everyone likes ice cream. Okay, so in a sense, everyone refers to a person, right? So we can say define a set P of persons, okay? And then let's define a predicate likes of X to say X likes ice cream, right? Okay, so now with this, can someone tell me how I can write this down? If you want to lift your hand, and I'll let you go, or if nobody wants to lift their hand, then you can try, right? That's how we learn. Okay, good. Let's, okay. Yeah.
Say there exists n or something in the set of P.
Okay, there exists n in P. Okay, is that what you meant?
Yeah.
Okay.
I guess such that
yeah,
L of n is false.
Okay, so not of L of n.
Yeah.
Right? Okay. So not everyone likes ice cream. The word everyone sounds like it's a for all quantifier, right? So does it, okay, first of all, let's ask, does anyone think this is correct, or let me ask, does anyone think this is incorrect? This is not the correct translation of that English statement. Is that, does anybody think that? No? Everybody thinks this is correct? Okay, so go ahead.
Oh, well, I'm just a little confused. Why is n being used there? Is n just like kind of like a variable we can always use? Or
well, I mean, variables, the name of the variables don't matter, right?
Oh, okay.
So we are saying that there exists a person
Mhm.
that does not like ice cream. That's the, so what the statement,
Okay.
if you want to turn this back into English, then we are saying that there exists a person, right? So this is what this whole thing means. There exists a person N that does not like the ice cream, right? That's what it says. So is that a correct translation of, is it the same thing as not everyone likes ice cream?
No, I feel like that one fits the second one better. I feel like for the first one to be correct, you have to do like for all people, there exists like, or there's like a set of people that doesn't like ice cream.
Okay, so can you say this, okay? For all N belonging to P,
There exists.
okay. So again, let's read this literally, right? Not, right? So let's leave the not out and then let's see what is here. Everyone likes ice cream, right? So we can translate that into for all N belonging to P, L of N, right? So we are saying we just took this part, right? The not is still there. So then we could put a not outside, right? So we break up the statement and then we consider the innermost part, which says everyone likes ice cream. And then we just turn that into a for all formula, right? So for all N likes N. Does it make sense to have a question on that? So somebody points out that this is a close match for the first formula, and this is a better match for the first statement, right? Does anybody not see that? Or does any, okay. Okay. Is this simple enough, or because I'm not entirely sure how many of you are following this. So if you don't follow this, ask a question and hopefully I'll figure out, you know,
Yeah, I have a
explain
question.
it differently and hopefully you'll get there. Yes, please.
The not, does that apply to the entire statement or only the for all sign?
Your audio for some reason I didn't get it well. Can
The
you
not sign, does it, can you hear me?
go ahead?
Does the not sign apply to the entire statement or only to the for all sign?
So for all sign, what is the meaning of negating a for all sign?
Not all?
Now, generally speaking, right? So, you know, think of expressions. I can, if you have a product, I can negate the result of a product. But there is no such thing as negating the product operator itself, right? It's something similar here, right? So for all is not something you can negate. Except, maybe in your mind, you may have some interpretation of what it means to negate a for all, but in reality, you're always, negation is to be applied to something that is either true or false, right? So which means that it should be applied to the whole formula, right? Because it's a full formula that is either true or false. So only something of the type true or false can have negation applied to it. Okay. But I think you have some intuition behind your answer, and I think we'll get to that in a few minutes. But I think technically we just want to say that, okay, negation should be applied to Boolean type values, and only the entire formula as a Boolean type. For all is just some operator. So now let's ask the question. So let's keep this on the side. Let's just look at these two English statements. We know English well enough to say whether these two mean the same thing or not, right? Who thinks that they have different meanings?
I think if you look at them literally, then the meanings would be different.
If you think, right?
I
Can you
think,
say that again?
yeah, I think that each, for the two statements that were just made,
Yeah.
I think they would not be the same exact meaning.
In what case are they not going to be the same? Give me an example where the two are not the same.
I was going to say, like, the first one seems like, seeing as it negates only ln, like that would be like only
No,
like
don't look at the formulas. Just look at the English. Okay,
okay,
because
then those are
we understand that
technically
formula,
equivalent then.
understanding the formula takes a little bit more time, but let's just look at the English.
Yeah,
Then what is
would
your
probably
answer?
be. I guess those would be, like, they would technically be equivalent. Yeah.
Right. So let's take another example. Okay, let's leave this these first two out, and let's take this statement. There is no one who likes being mocked. Okay, how do I say this? And once again, let's use P to refer to a person, and let's use the predicate M to being mocked. Oh, I'm sorry. M to liking being mocked. Right? So this is M, okay, and the person P remains the same. Okay, so can someone tell me how to translate this statement into a quantified formula? Lift your hand, maybe I'll be faster this time. Okay. Yeah.
So taking it as it says. So
I'm sorry, once again, because I was clicking on someone and then it changed. So Michelle, can you
okay.
go ahead? I'm sorry. Yeah.
Okay, I said like not there exists.
Can you maybe move just a tiny bit closer to your microphone?
Can you hear me now?
Yeah, great.
Okay. So not like the negation of there exists in
Okay.
the set of P.
Can you just try to say the whole formula so I can
Okay.
write it down and then we can correct it if necessary.
Okay, so like the negation, like not there exists.
Okay, not
It's
that
set of
exists.
P such that L of M.
Right? Because we use M to capture this whole thing, liking
Yeah.
being mocked. Right? So I got what, did I get you right?
Yeah.
Okay. So there is no one, right? So this no is not, okay? And then one who likes being mocked is M of n, okay? And there exists no one, right? Which is not of there exists n, right? So again, if you read this out as English, it says there exists no person, right? There exists, or rather, not of there exists a person who likes being mocked, okay? And that's what we would, when we say it in English, it'll be there is no one who likes being mocked, okay? So let's take this statement and let's say what it says. This seems a little bit easier to translate, right? Everyone dislikes being mocked. Let me see, somebody else. Anyone else who wants to answer? Okay, let's see. Yeah, Greg.
I would say for all n in P, not m of n.
For all n in P, yes?
Yeah. Not m of m. M of n.
Okay. So of all the people, okay, for everyone, right? So this says everyone does not like being mocked, right? Okay, now, once again, compare these two and tell me, again, looking just at the English of those two statements, do they mean the same thing or not?
I think they're both the same.
Right? Okay, so you can see a pattern emerging, which is saying that so okay, let's see where yeah. So this is the pattern that's emerging, right? So for all is somehow it's equivalent to not of that exists, not of something, okay? So okay, so whenever you have, let's take this down, there exists n, p, not L of n, okay? Or let's take this, okay, for all n in p, L of n, right? So not of for all n in p, so we said this is not of for all n in p likes of n, right? So let's apply this identity which says that for all is the same thing as not there exists not, okay? So we are going to say, so we are going to apply that on that, okay? So let's put a parenthesis here and just work inside the parenthesis, okay? So for all is going to become not of there exists n belonging to p, not of L of n, okay? So we have replaced this for all n with a there exists n, and then we put a not before the there exists, and then we put the not to the right to whatever is in the body of the existential quantification. You see what we are doing? Now you can, of course, cancel out these two negations, right? Because not is just true, right? So not and not cancel out. So you end up with there exists an n belonging to P, not of L of n, right? Which we said is the translation of that statement. Okay? So whatever we understood, whatever we did by understanding the English statements and realizing that these two are mean the same thing, we can also do that using the formulas by using these two identities. Okay, by saying that for all is the same thing as saying not there exists not. Okay. We can do the same thing here. So this is not of right. So this is the statement. And once again, we can replace this there exists by not for all not. So again, let's put the parenthesis out here. So we have not, and then this becomes not for all n belonging to P, not of M of n, right? So we have replaced there exists by not for all not. And once again, these two nots will cancel out, and you have for all n belonging to P, not of M of n, right? Which, if you look back at the previous slide, we would have said is the translation of this statement. Okay, so so there is a simple way to take negation and push it into a formula, right? So that's what. So although we saw this as a replacement of there exists by for all and so on, the other thing that we did was that there was a negation at the outermost level, and we were able to push that negation all the way inside by using these two operations. Okay, so why would you want to do that? Well, sometimes one form of sometimes it's easier to understand one form versus the other form, and then you want to but you're guaranteed that these operations are meaning preserving, so you can use these simplifications to hopefully get at something that that's easier to understand. Okay, so in your next homework, right? So we will, just like you had a homework on prepositions, you will have a homework on predicates, where you will be asked to do things like take an English statement, turn it into a quantified formula, or vice versa, right? And then do things like is this formula equal to the same as some other formula, and so on. Okay, so when you work out those problems, you will your understanding of these quantifications and so on will you'll get more comfortable with these quantifiers. So let me okay, let's summarize this unit. So we introduced predicates and quantification, right? And then We talked about satisfiability and validity. These are basically the same concepts, except that in the case of propositions, the propositional case, the only values that you're assigning are true or false. Whereas in the case of predicates, you have parameters that may be from any domain, like integers, floating point numbers, and the set of all people, and so on. And so when you talk about what values these variables can take, they can take values other than true and false. But ultimately, when those values are given, you still have the formula evaluates to true or false, and then you say it's satisfiable if there is some way to assign these variables such that the formula becomes true. Whereas validity means that for every assignment of these parameter values, the formula is true. Okay. So then we talked about quantifiers, and the most important part of that is understanding these quantified formulas, which basically means that you are taking these formulas written in English and turning it into formulas in logic, and vice versa. Okay. Then we talked about order of quantifiers and negating quantifiers. Any questions? Okay. So again, in computer science, what we are trying to do is we are trying to become more comfortable in stating, in specifying what we want in a formal and more precise way, right? And logic is a way of making ourselves precise and unambiguous, right? So that if you say you want someone to do if you say that someone, if you want to produce requirements for some software package, you want to say it should do X when you do Y, and so on. So you want to make sure that as much as possible, these requirements are precise and unambiguous, right? And so we are learning the language of logic, because that language is unambiguous, right? And it allows us to say things precisely and avoid the possibility that different persons will interpret this differently and then end up producing solutions that are different from what we wanted, right? So that's sort of where what all these is aimed at. Any questions? Okay, so again, what I want to do is I want to hand out homeworks as and when we finish the units. So just in like the last homework, we had roughly 2 units into one homework, and we will do something very similar this time too. Okay, and so we'll move on to the next unit, which is sets. Okay, so any questions on the last unit? Okay, so let's. So all of us, know what sets are, okay? But we may not remember everything about sets. And the purpose here is to refresh you on some of the set related terminology and operations and so on. Okay, so informally, a set is nothing but it's a collection of things, right? Sometimes they say objects. When a computer science person says object, that means a little bit has a more specific meaning. So I just said things. Okay, so so here is a set A, which consists of maybe pet names. Set B, which is a set of colors, and set C, which is a set of sets. Okay, so nothing says a set should not contain sets. Okay, so most of you know that the order of elements in a set does not matter, right? So you can write this. If you can change, you can flip Shells and Alex and Tippy and Shadow, and that doesn't change the set, right? So the order is not relevant for saying what is in the set. Okay, and you also have the property that there are no repeated elements in the set, right? So you can't say right, that is not a set because you have elements repeating. Okay, so in a set there are no repeating elements. Okay, so these are two elementary things about sets. So many times we want to describe infinite sets, right? Where the number of elements is unbounded. Okay, so here is an example, and here is a set of integral multiples of 3, right? So we want to have a compact way of specifying this sets like this, and for that we use something called the set builder notation, which most of you have probably seen before, right? So the set builder notation is of this form. You have something like x such that x satisfies some condition. Okay, so therefore this is going to be a predicate that takes x as a parameter. Okay, so this is why we talk about predicates before coming to sets, because we want to be able to define sets using predicates. Okay, so an even more compact way of writing this down is to say this set T consists of elements of the form 3n, where n is a member of n is a natural number. So this is the notation we will repeatedly use to refer to the set of natural numbers, right? Which is 0, 1, 2, 3, right? So the set builder notation allows us to precisely specify the elements of sets that may have infinite number of elements. Okay, if they have a finite number of elements, we always have the option of explicitly listing those elements, right? Although that may not be the most compact way of representing the set, that option is available. But if it's an infinite set, we don't have that option, and so we need to either describe the set in English, or we can describe it, precisely using a predicate, right? So what we are doing in a set builder notation is we are using a predicate to define a set. Okay, define the members of a set. So you may not, I don't know whether you have heard that, this, you have seen, I think most of you would have seen this notation or not. Tell me how many of you have seen a notation like this, even if the terms like predicates were not used, this kind of notation, X such that, such an, something about X, right? So this is a familiar notation, right? How many people have seen this before? You can lift your hands. Once in a while, I will ask a lot of people to lift their hands, but okay, good. So I can see. Okay, so there is some fraction of the class that's lifting their hand. So am I to assume that 3/4 of the class has not seen this kind of a notation before? X such that something about X? No, okay. So I'll again, I have this feeling that, this was all done some point along, during your school, but it's been so long ago that it's no longer in your working memory, right? Anyway, that's fine. There is no need to know this before because we just said, we just explained what it is, right? So that's, so very often, we work with, most of the time, we are going to define new sets based on existing sets. So for instance, we start with the set of natural numbers, and then we are going to define a subset of the natural numbers, such as multiples of 3. So, so in order to do that, let's, define some notation. So phi, which is the empty set, right? So we often use the empty set. The set of natural numbers, which we have seen many times. The set of integers, which means that the numbers can be both positive and negative, right? So it's like natural numbers, except that you take every natural number and negate it, and now you have the set of integers. Then we have rational numbers, which again, if you recall from previous lectures, rational numbers can be expressed in the form P by Q, P divided by Q, where P and Q are both from the set of natural. I'm sorry, that's not correct. What should I have said here? Both are drawn from?
The reals. The real numbers.
I
Then
think
what
it
is
should be the rational.
irrational then?
Integers.
Yeah. So I think you had in mind, negative numbers should be allowed, but you said real instead of integers, right? So P and Q are integers. So rational numbers are numbers which can be expressed as P by Q, where P divided by Q, where P and Q are both integers. Okay. And then the set of real numbers, right, which include not only the rational numbers, but also irrational numbers, right? So we have, we can write down subset relationships. So we can say the empty set is a subset of natural numbers, right? Because empty set is a subset of every number, right? Every set. And N is a subset of Z, right? You can see that N contains subset of the elements from Z. Z itself is a subset of Q, and Q itself is a subset of R, and R itself is a subset of C, right? So anyway, the main point here is that there exist these sets, and we'll use these symbols to refer to these sets. Okay, and of course, I'll remind you a few times. Okay, so let's define some of the operators that we use commonly, and of course, all of you have seen this membership operator, right? So we can say 2 belongs to the set of natural numbers, and we can also say square root of 5 does not belong to the set of rational numbers, right? Because square root 5 is irrational, just like square root 2 is irrational. Okay, so we have the set union notation, and again, I will assume that everybody knows what union and intersection are, but that doesn't prevent us from precisely defining what these are, right? A union B is defined as the set of elements that either belong to A or belong to B, right? So that's why we say it's X such that X is a member of A or X is a member of B, right? That is the definition of the union of A and B, okay? Intersection is very similar, except that instead of the or symbol, we use the and symbol, right? So the element should A intersection B consists of X such that this X is a member of both A and B, right? So that's the definition of intersection. And we can go on to define what is a subset and what is a proper subset. Okay, a subset means that every element of the set is also present in the other set, right? So in this case, we say A is a subset of B if every element of A is also there in B, right? So this is how we understand the term subset. A proper subset means, okay, you have the subset relation holding. In addition, the two are not the same. Okay, so this is like a subset or equal, right? So A subset or equal to B is one way to read this symbol, right? Subset or equal to. Whereas this is a strict or a proper subset, which means that B contains at least one element that's not in A. Okay. And finally, we can define the notion of a set difference. Okay, a set difference for which we use the minus symbol, right? So A minus B consists of all elements of A, right, that are not in B. Okay, so we think of it as minus because every element that's in B, then those elements are removed, right? So we subtract the elements of B in a sense from the elements of A, right? So that's why we call this as a set difference, right? So for instance, if you have, A, B, C minus B, D equals what? Okay, so somebody wants to answer this question?
AC.
So by definition, you only have to worry about elements that are already in A. So D is in B, but since it's not in A, you don't even have to think about it, right? So you go through the elements of A, okay, and then check if those elements are in B. So A is not in B, so it gets in the difference. B is in B, so it gets thrown out. C is not in B, so it gets retained, right? So that's the set difference. So again, intuitively, we remove the elements in B from A. Okay. If some element of B is not there in A, we just ignore that. Okay. So that's the. So often we'll be asked to show that two sets are equal, right? And we can start from these definitions and mechanically show that two sets are equal, okay? And once again, if the sets are finite, you can essentially enumerate the elements and then say, hey, this set contains 3, 4, and 5. That set also contains 3 or 4 and 5. Therefore, the two sets are equal, right? But sometimes the sets are defined, differently, and it's not. It may not be that obvious that the two are equal. Then there is still a mechanical process for showing that two sets are equal. What you do is that you take, you establish an implication that if X belongs to A, then X belongs to B, right? So you take any element that's known to be in A, then show that it also is in B, and then you turn it around and then say that any element that is in B is also in A. Okay, so we will get to these examples, later on, but I just wanted to point this out to basically say that we have complete definitions of these operations, and based on these operations, based on these definitions, we can start understanding what it means for an element to be in the union, intersection, difference, and so on. Okay. So another way to show that two sets are equal is to say that A is a subset of B and B is a subset of A. If this is true, then it must be the case that A and B are equal. Okay. Sometimes we are working with sets that are all subsets of the same large set, right? So for instance, we may talk about even numbers and odd numbers and so on. So in that context, the larger set is the set of natural numbers, right? So this larger set is, is often called a universal set, to say that it defines the universe from which the elements of other sets are created, right? So it's a universe, and everything else has to be, a subset of this. Okay. So in the presence of a universal set, we can define the notion of a complement. Okay, so you define A bar, right? That's what we call it, A bar. A bar is the set of elements that are not in A. Okay, so it's almost like a negating a set. Okay, so the complement is, again, when we say in English, we say complement. Again, if you're talking about logical statements, complement means we are negating, right? So similarly, when we say complement a set, we are essentially negating the set, and we can express it more formally as the set difference between the universal set and the set A. Okay, and notice that because it's a universal set, you're never going to have a situation where there's an element that is in A but that's not in U, right? Because every element in A must, by definition, be in the universal set. And therefore, U minus A is nothing but X, all the elements of U that are not in A. Because any element that's also in A would have been removed by the set difference operation. So these two statements are essentially two different ways of saying the same thing. Okay? So so when we were talking about proposition and propositional formulas, we mentioned that or and, right? So this was part of your first assignment, right? First homework, to show that or and are, no, I'm sorry, I'm misspeaking. Okay, so what is the meaning of associative? Can someone tell me what is the meaning of associative operator?
The way you group them doesn't change the meaning.
Can you, yes, but can you say it in, okay, sure, no problem. So an operator is associative, okay, if okay, so we say that an operator okay, so let's invent a name for the operator, right? So that's a plus with a circle around it, is associative if equal to what?
A plus B in parentheses plus C.
Yeah. So I'm sorry, again, I'm losing track of where I am. Okay. So so in other words, the way you parenthesize is not important. Okay. So can you tell me an arithmetic operator that is associative? Give me an example of an arithmetic operator that is associative and one that's not associative. You want to lift your hands or you want it?
Multiplication is associative, but subtraction isn't.
Okay, so for instance, we know that 5 plus 3 plus 7, you know, it doesn't matter whether you call it, whether you put it this way or you, right? So those two are same. But if you have a minus, okay, now is that, so this equals what? 9, right? Because what is in the parentheses becomes -4 and you subtract -4 from 5, you get 9. Okay, so whereas here, this is 2, 2 minus 7 is -5, right? So so in the case of sets, both union and intersection are associative, okay? And the reason is that both union is defined in terms of the disjunction operation, and intersection is defined in terms of conjunction operation. And so since both disjunction and conjunction are associative, therefore it follows that union and intersection are also associative. Okay, you can understand it that way, or you can also understand, you know, from your intuitive understanding of what is a set union and set intersection, that can also help you convince yourself that these two operations are associated. So they are also commutative. What does that mean? What does that mean? So when I say something is commutative, what do I mean?
A operator B would be the same as B operator A.
Right. So the order doesn't matter. And once again, if you want examples, you can use plus and minus, right? So for plus, it's commutative, right? 5 plus 3 is the same as 3 plus 5. But for minus, it's not commutative. 5 minus 3 is positive and 3 minus 5 is negative, right? So the two are not equivalent. But again, both union and intersection are commutative. And once again, you can either understand it from your intuition for union and intersection, or you can simply go from the definition of union and intersection in terms of these Boolean operators, or and from these or and operations, you can figure out, okay, if these are commutative, then these must be commutative too. Okay. Then there is a distributive law. So what is a distributive law? For a distributive law requires two operators, right? So we have A, okay. So let me just use this. Okay, a circle with a dot inside. That is the second operator. Okay. So what, can someone lift their hand to tell me what a distributive law means? Okay, Frederick.
So in this case, it would mean that A circle dot B circle plus, or in those that in parentheses, circle plus A circle dot C.
Right, so we just push the dot operation inside the parenthesis, right? And then we just we take, so essentially we are changing the order of the operations, right? So here it says do the plus first and then the dot, whereas here we have done the dot first and then the plus, right? So the distributive law says that I can change the order in this way and the result won't change. Okay, so once again, if you take if you replace dot by integer multiplication and circle plus by integer addition, then we know that this is a valid formula, right? But of course, if we call the circle dot as integer addition and circle plus as integer multiplication, right, then it doesn't work, right? So in the case of integers, you have this property that multiplication distributes over addition, but addition does not distribute over multiplication. Okay, but in the case of Boolean operators like or and and, right, it's symmetric. Or operation can distribute over and operation can also distribute over or. Okay, and because of that, because union and intersection are defined using or and, you also have the property that union distributes over intersection and intersection distributes over union, right? So union distributes over intersection, intersection distributes over union. Okay. And once again, you can start from the definition and you can, work through the steps to convince yourself that these two formulas hold. Okay. And finally, we can talk about De Morgan's law, right? And again, De Morgan's law is there are various versions of it, and one of them is in the context of Boolean formulas, where we say, not of P or Q equals not P and not Q, right? And then there is a version of it which operates on sets, where the negation becomes the set complement, right? And R becomes union and becomes intersection and so on. Okay, so they are all very similar. There is a lot of similarity between set operations and Boolean operations. And again, this arises from the very fact that these set operations were defined in terms of Boolean operations, right? It's not accidental. We have defined the set operations in terms of Boolean operations. So it's only natural that the formulas will also be similar between the Boolean domain and the domain of sets. So any questions? Okay, so now I think everything we have talked about so far are concepts that you probably at least vaguely recall from some time in the past. But a power set is something that you may or may not remember. Okay, so what is a power set, right? A power set is a set of subsets of a given set. Okay, so if you have a set 1, 2, 3, okay, we can write out its power set. Ugh, I can't even write this script P. Okay, let's try this again. I'm going to just not use a, right? So let's use this script P, which is somewhat easier for me to write, okay? So you always start with the empty set, okay? The empty set is denoted phi. Sometimes you can also, just an empty braces is also another way to denote the empty set, okay? So then we can list subsets of size 1. Right? Then we can list subsets of size 2. And then we can list subsets of size 3, and we are done, right? So the power set of a set consists of all of its subsets, okay? So power set always includes A, and of course it always includes the entire set, because a set is a subset of itself, right? So the smallest element is the empty set. The biggest element is the whole set itself, okay? So we use this notation, two vertical bars around a set to refer to the size of a set, okay? So given that A is of size n, what is the size of the power set of A? Let's take this example, right? So we have a set of size 3, right? And then we have how many subsets? 8, right? So we have 8 subsets. So let's take something smaller so that we can see a pattern maybe. So let's look at the power set of a set with 2 elements. Then you have phi 1, right? So this is 8 elements. This is 4 elements. So can you tell me what could be the size of the power set of A?
Is it n factorial plus 2?
N factorial plus 2. Okay, let's see whether that works. So what is 3 factorial is 6. Okay, and 2 factorial is 2. It certainly works for this case, but it won't work for n equal to 4. Okay.
Alternatively, they're both powers of 2. So we
Okay.
could say a 2 to the size of A power.
Okay. Now, that is the correct answer. Now, can someone try to reason through this? Why should this be the case? Does somebody have, I will ask someone to unmute, but let's see what.
Well, for each member of A, for every member of the power set of A, each member of A is either in it or not. So there's 2 possible states for each one. So if you have n things, each with 2 possible states, there are 2 to the n possible combinations.
Right. So let us say that A contains elements A1, A2, all the way to AN, right? So now we want to construct a subset of this set, okay? So that subset for each element, right? It can either include that element or not, right? So to get one of the subsets, you have to decide for each of these elements, A1, A2, up to AN, whether that element is included in the subset you're constructing or not, right? So for each of those choices, right? So this is included or not included. So this is included or not included, right? So there are 2 choices for each element and n elements. Therefore, these are n independent choices, each choice being having one of 2 values. So there are n elements here. So 2 multiplied by 2 up to n times gives you 2 to the power n. Okay. So if you understand this well, great. If you don't understand this well, that's okay. Don't worry about it, because one of the things that we are going to learn in this class is how to do counting, right? So how do we estimate the number of number of ways of doing something, right? And so we will get to this, we'll revisit this at some point. And so if you don't understand exactly how it works, that's okay. You can still remember that this is the you can remember that that's the formula for the number of elements of a power set. Okay, and then we can go from there. So let me stop here, and your next homework is going to be again on predicates and sets. Okay, and we aren't quite finished with the sets today, but we will finish it in the next lecture. Okay, so are there any questions? So you'll have your recitation the same way like last time. So take your questions about the homework or any other questions about the material that we have covered in the class, right? So you bring those questions to your recitation and the TAs will do their best to help you. And if you don't have your answers, your questions answered there, then you can always come back to them during their office hours, or you can come back to me during my office hours. Yeah, but make sure that you don't let things, go away from you, right? So if you lose, if you find yourself lost, you need to sort of, fight back and get into it, right? So if you let things drift away from you, then it becomes, very hard to catch up. So make sure that your goal is to make sure that, so you want to make, you don't want to let me move forward unless you have understood what we have covered in class, okay? Because if you let me, take off, then I'll take off, right? And then it becomes quite difficult for you to follow, and also the classes become useless. So you need to speak up and you need to ask questions. And again, always keep in mind that I have been doing this for a very long time. So sometimes I won't understand why, something is difficult to follow. And so, try to explain, try to ask questions, and eventually I'll figure out why. And then I'll hopefully give you the right answer. But you need to also keep at it and keep pushing me until you get the answer that you need. Okay, so take your 10 minutes off and then, get back to your recitation, and then I'll see you on Thursday. Okay. If anybody has a question, I'll hang around for some more time. Otherwise, feel free to hang up.
Is 2 to the absolute value of A the same thing as 2n?
So we have said A, it's not absolute value of A, that's called size of A.
Okay.
Is n, right? We define the size of A to be n, right?
Okay. Thank you.
I have a question.
Sure.
So what was the definition of a power set? I understood everything, and then you started going about power set, and I kind of understood it, but then I kind of like said, okay.
That's the definition.
Power
The
set.
set of all subsets of a given set.
Okay, so it's like all the possible combination that it could take on. Okay. And like 1, 2, and 3, those, like, could those also be sets? Those, like, it's like a power set could be like the combination
You can
of
also
sets.
define power set of power set, if that's what you're talking about. Is that what you're talking about?
Yeah, like how like there's like.
So for instance, you can take this set here, right? Which is the power set of 1, 2, 3, and you can say, hey, what is the power set of this set? Yeah, so you can have a power set of that set.
Okay. And by the size exactly, I was just wondering, like, what was that referring to exactly?
Size is the number of elements.
Okay, so the size was just like 1, 2, 3, 4 right there. And so the size on the next slide, it says the size is n. So you're just saying 2.
So let's call the size of this set A to be n, so that we can write something compact like 2 to the power n instead of something like this, which is a bit
okay. I think
a bit harder to read.
I think I got it now.
Yeah.
Thanks.
Okay. Good.
Thank you. Have a good day.
Yeah, you too.